Using vectors, verify that the diagonals of a quadrilateral bisect each other if and only if it's a parallelogram. Okay, let us begin. First, we need to understand the problem. This is a biconditional statement as it uses if and only if. Now that means we need to prove two parts here. So here we will show that if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. So this is the first part. We will also need to show that if a given quadrilateral is a parallelogram, then the diagonal of the parallelogram must bisect each other. If we can show both the two statements are true, then the given biconditional statement, the diagonals of a quadrilateral bisect each other if and only if it is a parallelogram, is going to be true. Let us begin with the first part. So here we will start by considering a quadrilateral ABCD. Now for this particular quadrilateral, we're going to define the position vector of each of the four vertices. Now to define the position vector, we need a origin of some coordinate system, and if we join O and point A, then it's going to be a vector going from O to A, and that is going to represent the position vector of point A. Similarly, we can join point O and point D, point O and point C, point O and point B with a vector directed towards each of the vertices, and those are going to be the position vector of each of the four vertices. So here we're going to consider the position vector of vertex A to be denoted by the vector A. Position vector vector B to be B, position of vertex C, let it be C vector, and position vector vertex D, let it be D vector. Now our goal will be to show that ABCD is a parallelogram by considering the fact that the diagonals of the quadrilateral ABCD bisect each other. So let's do one thing, let's join the diagonals AC as well as BD. Let's say the diagonals AC and BD of the quadrilateral ABCD bisect each other at the point E. So here we can say that E bisects AC in the ratio 1:1 internally. So that means we can apply the internal section formula to define the position vector of point E. Similarly, E also bisects BD. That means it divides BD in the ratio 1:1. So here also we have an internal section formula. So we will begin by first defining the position vector of E by considering the diagonal EC. So here we will consider the fact that E is bisecting AC. That means it's dividing AC in the ratio 1:1 internally. So here OE vector will be simply equals to, we'll take this 1 and it will get multiplied it with the position vector of the vertex C. So that means we have 1 times C vector added to, this one will get multiplied with the position vector of vertex A, so we have 1 times A vector, whole divided by 1 plus 1. So that means we have A vector plus C vector divided by 2. We're going to label this as number 1. Next, what we'll do, we will use the fact that E divides BD in the ratio 1:1. Again, we can use the internal section formula. The OE vector is going to be equals to B vector plus D vector whole divided by 2. So let this be equation number 2. Therefore, using equation number 1 and 2, we can say that A vector plus C vector divided by 2 equals to B vector plus D vector divided by 2. Fine. So let's rearrange it. So here we can first factor out 1/2 from both sides to get A vector plus C vector equals to B vector added to D vector. Or we can have here rearrange the terms to get A vector minus B vector equals to D vector minus C vector. Now A vector is nothing but OA vector. B vector is OB vector. This will be equals to OD vector minus OC vector. By definition, OA vector minus OB vector is simply the vector BA. And OD vector minus OC vector, that is the vector CD vector. Now let's go to a diagram. We have BA vector equals to CD vector. So BA vector means it's a vector going from B towards A. This is equals to the C vector, C going from C to D. As we can see here, that BA vector equals CD vector. That means that, so here we can say that BD vector equals to a BA vector equals to CD can mean two things. It means that the magnitude of the two vectors are equal, so that means they are equal in length, and we can also say that BA is going to be parallel to the length CD. Now, this is true for the case of a parallelogram. So we have successfully showed that ABCD, the quadrilateral ABCD, is going to be a parallelogram if the diagonals bisect each other. Okay, so our first part is done. This implies that ABCD is a parallelogram. If the diagonals bisect each other. So our first part of the proof is done. Now we'll have to go to the next part of the proof, where we need to show that if a given quadrilateral is a parallelogram, then its diagonal bisect each other. Okay, so let us begin. Now we'll begin by considering a parallelogram ABCD. So it's already given here that the quadrilateral ABCD is a parallelogram, which means that we can consider two of its sides to be equal. Now before that, we'll also have to name the four vertices of the parallelogram with respect to their corresponding position vectors. So the position vector of point A will be A vector. For B, it will be B vector. For C, it will be C vector. And for D, it will be D vector. So we're going to use the fact that since ABCD is a parallelogram, so this implies that the side AB, that will be exactly equals to the length DC. Or in other words, we can say that AB vector must be equals to DC vector. Now in terms of the position vector, AB vector can be expressed as OB vector minus OA vector, and DC vector can be expressed as OC vector minus OD vector. Now this will be equals to, now what is our OB vector? So OB vector is going to be a B vector, so where B vector minus A vector, that will be equals to OC vector, so the C vector minus D vector. This will be equals to, now we can rearrange the terms to get A vector plus C vector added to B vector plus D vector. Now we're going to divide both sides with 2. So we have A vector plus C vector whole divided by 2, that equals B vector plus D vector whole divided by 2. Now the reason why we're making the vectors A plus C over 2 equals to the vector B plus vector D added or divided by 2, because here A plus C over 2, that's nothing but the position vector of the point E, which is going to divide AC in the ratio 1:1. This is the ratio 1:1, and the position vector of point E, that's going to be A vector plus C vector over 2. And we have this equals to B vector plus D vector over 2. So that means if we join the diagonal BD, then E divides BD in the ratio 1:1. So here the position vector of E is going to be given by B vector plus D vector divided by 2. Now this particular equation tells us that the position vector of the midpoint of AC, so this will be exactly equals to the position vector of the midpoint of BD, which tells us that the diagonals are bisecting each other. This means that the diagonals of the parallelogram bisect each other, and that's what we were asked to show, that if a given quadrilateral is a parallelogram, then its diagonal bisects each other. So we've successfully showed that as well. Now we can combine the previous statement that ABCD is a parallelogram if the diagonals bisect each other, and the fact that the diagonals of a parallelogram bisect each other. Therefore, finally, we can claim that thus the diagonals of a quadrilateral, so we're considering a quadrilateral, the diagonals of a quadrilateral is going to bisect each other, if and only if the quadrilateral is a parallelogram, hence proved.